Okay, guys, so there is what we call the notion of one-sided limits, okay? And if you look at figure 6 there, you'll notice that as x approaches 0 from the right-hand side, you'll see that that limit tends to 1, the limit of that function. And as x approaches 0 from the left-hand side, the limit of that function is -1. So in that case, the limit does not exist because the left and right-handed limits are unequal, okay? Right, and the notation that they use is also the bottoms given there. So I assume you guys have gone through these very briefly. It's relatively easy to understand once you have an idea of the concept of a limit. So a limit from the, let me just show you guys here. In this case, we see here that the limit here is from the right-hand side, is x tends to 0 and is equal to 1. And then below there, we can see that the limit as x approaches 0 from the left-hand side is equal to -1, as is evident from the curve, okay? You can see that. And that's the notation. So from the left-hand side, we use a negative. And then from the right-hand side, we use a positive, okay? Right. So in that case, we say the limit does not exist because the left and right-hand limits are not equal, okay? Though they exist independently, but they're unequal, okay? So the limit therefore doesn't exist. And then there, right up there, the limits like these are called one-sided limits. And from the last section that we encountered, we know that the limit of a function as x tends to a is independent of the way x approaches a. The limit will exist if both one-sided limits exist and are equal, like I said. So in the case that we just encountered on top for this function here, the graph of this function, just from the graph of that function, you can see those left and right-hand limits are unequal and therefore the limit doesn't exist. So we therefore conclude that the limit as x tends to 0 does not exist, okay? And then below that, we have this figure 7, which deal with the square root function. And you guys know full well that the x-intercept there would be 3, because that function is defined only for x greater or equal to 3, because we can't have negative values for x under the third, okay? So, and the only way that x can approach 3 is from the right-hand side, okay? There's no way it can approach 3 from the left-hand side because the function is undefined for values less than 3, okay, for x less than 3. So, and then they use the appropriate notation, the limit as x tends to 3 from the right-hand side. Well, we just substitute x under that third, and the square root of 3 minus 3 is the square root of 0, which is equal to 0. So in that case, we have a right-handed limit only, okay? And then there's a discussion of this function here. It has two parts, one in the first and one in the second quadrant. And you guys can see that as x approaches 0 from the left-hand side, this thing shoots up to infinity, okay? Shoots up to infinity. And if x approaches 0 from the right-hand side, it also shoots up to infinity, okay? So you can see that case. So in that case, in both instances, the limit is equal to infinity, okay? So for that case, the function f of x equal to 1 over x squared, okay? And we write that as the limit as x tends to 0 of 1 over x squared is equal to infinity, okay? It's undefined, okay? Right. And then if you can look at the rectangular hyperbola, you can see as x approaches 0 from the right for the first quadrant. Look at the first quadrant, guys, okay? Look at the first quadrant. As x approaches 0 from the right-hand side, again, the function shoots up to infinity. However, as x approaches 0 from the left-hand side, it shoots down to negative infinity, okay? You can see that it goes down and down. It doesn't cut the y-axis, the negative y-axis. So in that case, you can see that those limits are unequal. The limit does not exist, okay? Right. And then we looked at a couple of activities the last time, and I trust you guys have gone through those again, because we need to get to the definition of a derivative of a function, okay? Right. And again, I'll use some, because I anticipated that you guys would have gone through this section. So I'm using some graphs or functions to illustrate some concepts, okay? So let's see quickly. So they say here, at the end of this learning unit, you should be able to relate the rate of change of a function to the gradient of the tangent at the point. Our tangent line is a line that cuts a curve at exactly one point, okay? And you should be able to differentiate simple expressions from first principles. We'll come to that notion of first principles, and we have to recognize the different notations for the derivative, okay? Right. So here the tangent question relates to basically the last time we discussed secant lines, say that those are lines that cut curves at two or more points. And then we also said a tangent line on the other end cuts a curve at exactly one point, okay? So here basically we want to be able to determine the gradient of a tangent line at a point on a curve. That's basically what the tangent question relates. Okay, so we want to know what is the gradient of that line, of that tangent line at a particular point, which will give you the gradient of the curve at that point, basically. So, and then we'll do some differentiation from first principles. So what I want you to look at is in the first instance, I just want to make this statement before we start looking at, let me just share the lined board with you before I come back to this. And the reason why I'm using the guide a lot is just to save some time with some of these fundamental concepts. So let's just get to the line board. I hope you guys can see the line board there, okay? Right. You guys would know that the gradient, you know the equation of a line y equal to mx plus c or ax plus b, or sometimes they write y equal to ax plus b. Same meaning here, m is the same as a, x is the variable x there, the independent variable, and then c is the y-intercept, here b is the y-intercept. So these two equations represent the same thing, they represent the equation of a line, okay, in the Cartesian plane. So, but we know that the gradient is m, or in the other case, a, okay? And we know that the gradient is given by the change in y over the change in x. So we know those concepts, okay? For example, if I give you a line, let's say I give you a line in the Cartesian plane. So suppose I give you this line in the Cartesian plane. Just draw the plane there. Suppose I give you a line like this. So there's my x-axis, there's my y-axis. And now suppose I give you a curve first, okay? And then I ask you, get me the gradient of the line. So let me draw a curve in another color, perhaps red. Okay, so suppose there's a curve going like this. Okay, I don't know what it's called, y equal to f of x, doesn't matter. This is the curve y equal to f of x. And now you ask me to get a gradient of a secant line between 2 points. Say these points are the points y1, x1, so that's x1. This is y1, of course it's negative. Okay, so I don't need to say negative y1, we know y1 is negative and x1 is negative. And then here, let's say we've got the x ordinate is x2, whatever it is, and we know that's positive. Let me just extend this plane here, guys. I didn't foresee this now. Let me just extend this plane here. So this axis, sorry. Just want to make sure that there's that. Just extend this axis. This y-axis, I just want it up there somewhere. Just that. Okay, great. So just to incorporate that y ordinate. Right, so let's get back. So we've got x2 and the corresponding y ordinate is y2, say. The corresponding y ordinate is y2. Now you know how to get the gradient of a line. let's say the gradient of a line between, or line segment between x1 and x2, between the points x1, y1 and x2, y2. So suppose you can draw that line something like that. Okay, right. Goes on and on to negative infinity, positive infinity, negative infinity. Now I ask you, listen, get me the gradient of that line. And you are given the x and y coordinates of the 2 points, okay? Then you can say the gradient of this line that cuts that curve. Now this is the line y equal to mx plus c, okay? We don't know what it is. But that gradient m is given by the change in y over the change in x, which is equal to, well, the change in y is y2 minus y1 divided by x2 minus x1, or y1 minus y2 over x1 minus x2, okay? Remember, this is the point x2, y2. This is the ordered pair x1, y1, okay? The order is very important there. So there's your gradient of a secant line. So this here, we call it the gradient of we call it m sec, meaning the gradient of a secant line. It's very important, secant SEC, okay, m sec, okay? So that's very important. So what we will be determining is, suppose we keep this point fixed here, the point x2, y2. We want to find out what happens as this secant line, y equal to mx plus c, as this point x1, y2 comes closer and closer and closer along the curve. It gets closer. Let me just use another color. So suppose that this point x2, y2 is fixed, and we want to observe what happens to this point x1, y1 as it gets closer and closer and closer along that curve, as it gets closer to that. What happens to that line? That line will shift now to change from a secant line to a tangent line, so that the distance between x1 and x2 tends to 0, okay? The distance between x1 and x2 tends to 0 because now x1 approaches x2. In fact, the point x1, y1 approaches the point x2, y2. And you will see naturally what happens. You will see that the secant line shifts now. It shifts accordingly as x, x1, y1, or any point xy approaches the fixed point x2, y2, for example, okay? So you will see the secant line shifts. In fact, it will come into this position roughly. Let me just try and draw this as accurate as possible. So it will shift from where it was, the secant line, and it will behave something, it will go something like this. Right? Because now it's at that point x2, y2. So that's what we're looking at, a secant line changing, the distance between x1 and x2 becoming closer to 0, the distance between y1 and y2, of course, also coming 0, right? And we can call this distance between x1 and between x1 and x2, we can call it h. That distance between x1 and x2, we can call it h. It's the absolute value, it's positive, okay? You can call it distance h. So we want to see what happens as h tends to 0. That is, as x1 tends to x2, okay? Or you can just say x, okay? Maybe arbitrary x, any x, not necessarily x1, any arbitrary x as it approaches x2, okay? Of course, as this comes closer to this distance comes close to 0. Therefore, h tends to 0, okay? And that's what we're looking at in that case, right? And here's that discussion, which I would hope that you guys have gone through. Let me just share the learning guide with you. So they start off with the following, the tangent question. They start off with the following. So there's a secant line, okay? There's the x that I spoke of, the arbitrary x, okay? there's the x, arbitrary x, and there's the distance between x and x plus h. The distance is h, as you can see on the x-axis, right? And then for the point x, you have the y value f of x, because this curve is the curve. The curve, that nicely shaped curve, not the line, is the curve y equal to f of x. And then for x, there's a y value f of x, which is plotted here. And then for x plus h, so this is at the point x plus h, there's a y value f of x plus h, okay? And then the difference in y is given by this here. The change in y is given by f of x plus h minus f of x, this here. The distance between that and that along the y-axis, okay? Distance between f of x plus h and the distance between f of x. And along the horizontal, the distance is h, okay? The distance is h because that's the distance between a point x plus h and a point x, okay? Arbitrary points, okay? So now, this is how, so what we have noticed was h tends to 0. H tends to 0 as the one point approaches the other point along the curve. H tends to 0, which means it affects f of x plus h also, right? So, and this is what we call the gradient of a secant line. It's the change in y over the change in x, but the y values change from f of x plus h, from f of x to f of x plus h, as you can see along the vertical axis. And the x values, well, the difference between the x values, as you can see along the horizontal axis, is h, okay? So the change in x is h, from x to x plus h, delta x, this here, delta x is equal to h, actually, okay? There's it in the denominator. So there's the change in y, the f of x plus h minus f of x, and that gives you the slope or the gradient of a secant line through the points A and B, okay? That's what happens there. Now, of course, this line will shift, the secant line will shift, and as it shifts, it tends to a point on the curve, a point xy, okay? Or some fixed point, AB, whatever. So here's the reading, guys. They say if we move B closer to A, so here, B is moving towards A now, not A towards B, like but it's fine, doesn't matter, it's arbitrary, okay? So here, the point B on top here moves towards A, right? So it means that along the x-axis, the distance h tends to get smaller and smaller and smaller, it tends to 0, right? And the secant line shifts to a tangent line, as I explained, because it now cuts the curve in exactly one point. Here it cuts the curve in 2 points, A and B, right? But B tends to A now, okay? So if we move B closer to A, h becomes smaller and smaller, it's getting closer to 0, and the secant line transforms into a tangent line. And the slope of the tangent line will thus be the limit, as h tends to 0, of f of x plus h minus f of x over h. And this formula gives us the slope of the curve at the point A, okay? Which is the slope of a tangent line at the point A, okay? So exactly the slope of the curve at the point A is exactly the slope of a tangent line. And it's a limit. The limit is h tends to 0, okay? Right, any questions there, guys, before we proceed? So I was just trying to really succinctly introduce you guys to the notion of the derivative, of course, the gradient of a tangent line, which gives us what we call the derivative, or let me say it like this. I try to introduce you to what we call the gradient of a tangent line, which at a particular point, which is also the gradient of the curve at that point, okay, at that particular point. So we saw the secant line changing as B approached A. So now the secant line becomes a tangent line and it cuts the curve at the point A, exactly one point. So that the gradient of that tangent line is actually the gradient of the curve at that point. That's what's happening basically, guys, okay? All right. Any questions there, guys, before we move on? And what we've just encountered now, the formula that I wrote down, the limit is h tends to 0 of f of x plus h minus f of x over h is actually what we call the derivative of a function, at the point x, okay? So and that is the limit as h tends to 0 of f of x plus h minus f of x over h. Okay, student Daniel. Okay.
Good evening. I just wanted to ask, my question is not solely based on today's lesson, but I just wanted to know if there's anywhere where we can get question papers to practice all these problems.
Okay, I'm not sure. I'm not sure if Ms. Prim can answer that, but I would just think that look on the on your MyUnisa, there should be the lecturer. I anticipate from other students' experience that there would be maybe some communication of that sort or some papers there that you can access. I'm not certain because I don't deal with those. Okay, I just facilitate this discussion, trusting that you guys went through the work. I'm not sure if Ms. Promina is in a better position to answer that. But then if you don't find any luck from us, maybe you can communicate with the lecturer concerned, okay?
Okay,
right?
Thank you.
Okay, I do not know who the lecturer is for this course, okay? Great. Okay, guys, any other content-related questions? I hope, because I really try to be very brief, because the supposition is that you guys would have read this, okay? Right. Okay, guys. Okay, there appears not to be any questions. So, okay, great. Right, let's move on now. So, what we've encountered, basically, what I tried to explain was this, and this is the notation. So, so there's my function y equal to f of x. The tangent line, the secant line becomes a tangent line at a point, right? So the derivative of the function f prime of x, which we write sometimes as dy dx. So if y equal to f of x, then the derivative of the function, let me just write this a bit below, then f prime of x, also written as dy dx. So this is the instantaneous rate of change of y with respect to x, because it's at a point. It's not an average like a secant line. This is defined as also, so you'll say I put two dots, meaning it's defined as the limit as h, the distance along the x-axis tends to 0, over f of x plus h minus f of x divided by h, right? So h tends to 0. H is positive, it tends to 0, okay? The distance, speak of distance as positive. So this h is the distance along the x-axis. There's a change occurring along the x-axis. And you can see as h tends to 0, you have f of x minus f of x, okay? Sometimes they also write this dy dx, or f prime of x. They also write it like this. They say it's the limit as delta x tends to 0 of delta y over delta x. So that's another way of writing that. So the change in y, which is given by this, right? Change in y, and the change in x is h. And there, delta x tends to 0, h tends to 0. So this means exactly the same thing. Okay, but we will largely work with this, the definition. So what I've circled now in red is basically the definition of a derivative of a curve, of a function. Okay, so it gives you the limit, and sorry, and I have to say if this limit exists. That's important. If this is important state, if this limit exists, the limit must exist. Okay, if this limit exists.
Sorry, sir.
Right. Okay.
Hello.
Right.
Hi,
Okay.
sir. Your screen is frozen, or is it my screen is the only one that's frozen? I can't see the
Is it
line.
people? Okay, people, can you see the? Okay, no, wait. I think I didn't share this. I didn't share it. I suspect I didn't share it. Sorry. Great. I should have shared the. Sorry, guys. Thanks for that. Wow, guys, you should have warned me. Okay. So what I was saying, if y is equal to f of x, like we had on top there or in the study guide, if y is equal to f of x and you have that secant line changing to a tangent line, so here we had the point, for example, in their case, they had the point B approaching the point A, say, then the distance h between x1 and x2 becomes smaller and smaller, okay? Tends to 0. So we say if y is equal to f of x, then f prime of x, which is defined as dy dx, which is defined as the limit as h tends to 0 of f of x plus h minus f of x, and this year, this bit here, f of x plus h minus f of x gives you the change in y. And this here gives you the change in x, this h here. So it's the limit as h tends to 0, the distance along the x-axis, because our independent variable is x, y depends on x, is the limit of f of x plus h minus f of x, the change in y, divided by the change in x, which is h. Sometimes, and this is important if this limit exists, but of course you guys don't deal with existence and non-existence of limits. For all intents and purposes, we'll always assume that the limit exists, of course. So, of course, alternatively, dy dx is also defined as the limit as delta x tends to 0 of delta x over delta y over delta x. Okay, this is the same thing. This means exactly the same thing. Okay, right. Okay. Any questions there, guys, at this stage? See in the chat. I think. Oh, so now I see it. Okay, great. Okay, sorry for that, guys. I failed to share the screen. I was just thinking I'm still busy with the guide, or I thought I shared it. Okay, right. So this is the definition of a derivative, which we will be using initially until such time that we encounter the rules of differentiation. Then we discard the definition temporarily or for some time. Okay. But initially, you must know how to use this definition: f prime of x equal to dy dx, which gives you the instantaneous rate of change of y with respect to x, which is the limit as h tends to 0 for f of x plus h minus f of x over h. So h tends to 0, right? H is the distance along the x-axis, right? So if there are no questions, then I would like us to look at maybe some activity, at least. And people, this is what we call the differentiation from first principles. Okay, so let me write it again. This is called differentiation from first principles. So this is subsection 2 of learning unit 3, right? So this is learning unit 3, and we're busy with subsection 2. So this is called differentiation from first principles. Differentiation from first principles. So what I gave you was the first principles definition. Right. Right, so and this is it. F prime of x. So we call it dy dx. So let me just say this. If y is equal to f of x, then f prime of x, or if you want to, dy dx, is defined as the limit as h tends to 0, f of x plus h minus f of x over h. This is the first principles definition of a derivative. Okay. So this is what the guys worked with initially until, and this concept was developed around the 1600s around 1660, somewhere there, 1666, independently by Leibniz and by Newton. So you have the German mathematician Leibniz in Germany, Leibniz, and then Newton in England, okay? So they came up with these concepts independently from each other, okay? Right. So, so we will now calculate some of these limits or these derivatives. And so let's do the first example and do some activity, okay? And you can look at the next example. So from your first example, we need to find, so it's example 1, and the function there is find the expression for the derivative of y. So now we will find these derivatives using the first principles definition. So from example 1, let me just show you example 1 there, guys. I was hoping you guys will always have your guides open in front of you and then you can check, okay? Let's see quickly. So I'm looking at this example. This one, yeah. Say find the expression for the derivative of y equal to x squared. And we will use this definition, differentiation from first principles, that limit as h tends to 0, that function, okay? Right. So we will now apply that to our function y equal to f of x equal to x squared, okay? So let me share, so this is the example 1. So we'll do that one, find the expression for the derivative, okay? So now let's just share the line board with you guys. There's the zone. Okay, right. So y equal to f of x equal to x squared. So now let's first find f of x plus h. We have f of x. F of x is x squared. Right, so let's get f of x plus h. Well, what this means is in the place of x, substitute x plus h. You squared x, so square x plus h, which is equal to x squared plus 2xh plus 2xh plus h squared, okay? Right, so there's f of x plus h. We've got f of x, we've got that. Now you want the derivative of this function, thus dy dx, or f prime of x, is equal to the limit as h tends to 0, of f of x. Now I'm going to use this. I'm going to use this formula now. Okay, you've got f of x plus h, it's x squared plus 2xh plus h squared minus f of x, this part here, which is here. And then we divide it by h, the definition, okay? Divided by h, there's it. Already we can see a cancellation occurring there. So it's the limit as h tends to 0. And then on top here, we've got a common factor h, which we can take out. It's 2x plus h. And that must be divided by h, and then we have a cancellation. And now we let this h tend to 0. And this is equal to 2x plus 0, which is equal to 2x. And there we have the derivative of x squared with respect to x is equal to 2x. Okay. Of course, we will use the power rule later on to get it immediately. We don't need to use the first principles definition. However, if in the exam or an assignment they ask you to use the first principles definition, which is the definition I gave you on top, this one here, then you must use that. You must get f of x plus h. That's the main step. The others are already there, okay? Right. Guys, before I go on to an activity, let me just check if there's any compelling questions there, guys. So that was the A part. Right, that was the A part. And I'm going to try and draw you the scenario actually as to what is happening here, okay? So that was the A part. Sorry, this was the A part. The B part asks you, let's look at the B part. Let me just share the screen and see what the B part asks. The B part asks you to, so we found the expression for the derivative of y equal to x squared. We found that expression. Now let's look at the B part. Right. Now they say determine the derivative of y equal to x squared at x equal to 3. So all you have to do, so we've got the derivative is 2x. So let me just share the zonal with you. Now we have to find that derivative at x equal to 3. Okay. Let me share the line board with you guys. Now at x equal to 3, y dx, guys, x equal to 3, y dx equal to 2 times 3, which is equal to 6. Okay, and if you look at that, really, the function that we started off is this quadratic function, and it looks like this. We don't need to do this, but just to make sure you guys are on track with what is happening in so geometrically in the Cartesian plane. So let's just see what is happening actually. Just see what's happening there. So geometrically, so you know the curve y equal to f of x squared. You know how that curve behaves from high school, right? There's your y-axis, there's your x-axis. Now you want x at x equal to 3. You wanted dy dx at x equal to 3. Suppose 3 is there, and this is 9. Okay, so this is the curve y equal to f of x equal to x squared. Okay, so if x is 3, y is 9, so we square that. So there's the point. So what we just got now, this answer of 6 at the point x equal to 3, we actually got the slope of this tangent line at that point x equal to, let me just use another color. We actually just got the slope of a tangent line at that point x equal to 3. That's what we just found now. And at that point x equal to 3, that slope is equal to 6, which is also the slope of the curve at x equal to 3. I can do better than that. See, so we just found the slope of a tangent line to that point. It cuts that curve at exactly that point. It's not nicely drawn, but I want you guys to imagine that it cuts that curve at that point, okay? Right, at that point, there's a black pen. The point bigger, so at that point, x equal to 3. At that point, x equal to 3. There's the tangent line, and it has a slope of 6, okay, which is the slope here. Right. So there's it at x equal to 3. So it cuts the curve at that point, okay? So that's geometrically what's happening, basically. Okay. Great. Right. Okay, guys, any questions before we move on? Okay, then we can perhaps look at an activity. I would assume that you guys have gone through some of these examples, like example 2, because there they use the binomial theorem to deal with all those, okay? I'm not sure if you guys have looked at this example. Let me just share. So there's it. So I'm talking about this example. If there's any one of you who had problems with this example, you should speak now, guys. Because basically, there you have y equal to f of x equal to 2x, or 2 times the square root of x, or 2x to a half. And they say find the first derivative of f with respect to x, or f prime of x, from first principles. Okay. So what they do is we have f of x and we need f of x plus h. So then we use an expansion because we've got two terms, x and h, and we use the formula for the binomial theorem. Okay. So then they order that. So I just wanted to check if you guys managed to go through this problem, this example. It's a very nice example, but it basically checks your understanding of the binomial theorem and also the definition of a derivative from first principles. Okay. Right. Of course, when the exponent is a fraction, you get an infinite number of terms. But of course, you can't write them all down. You just say dot, 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 dot. Okay. Right. So I think this is a good, if you can understand this example very well, then you guys are well on your way to understanding that first principles definition. Okay. Right. So can I just check, is there anyone that maybe tried the example? Okay, Joyce, student Joyce. Okay.
Good evening.
Good evening, Joyce.
Example 1. Why didn't we square 3? And then we said we said 2 multiplied by 3. Why didn't we say
let me
3 squared?
Let me just share the screen again and you can ask the question. Let me just share the screen again. Did I forget something? I hope I didn't forget something. Let me see. Where am I now? Zono. Okay. You said, why did we? Oh, remember.
Why did we?
Yeah,
Yes.
remember. Yeah, remember. They wanted the derivative of y with respect to x. We got 2x, right? We got 2x. This was our answer. 2x. So this was it. This was the answer. 2x, right? So now, at 2x, they want the derivative. They want the derivative at x equal to 3. So we use the derivative. This is the derivative. And it's 2x. And at x equal to 3, it's 2 times 3. Okay, the derivative. But the function value at 3 is 9. That's a different matter. Okay, the function value at 3 is 9. Okay, but this what you have here is a general formula for what we call the gradient of a tangent line to any point on that curve. And now they want to know at 3. So at x, say I ask you the gradient at x equal to 50, for example. Then it's 2 times 50 is 100 because it goes steeper and steeper and steeper, this curve. You see this curve goes like that, it goes steep. So the gradient will be steep, the gradient will tend to infinity as the x gets bigger and bigger and bigger. Okay. So the gradient is still relatively small at 3. You can see there, look at that slope of this line here. But as x gets bigger and bigger and bigger, you substitute into there. Suppose I ask you the point x equal to 1,000. Then the slope of the tangent line is 2,000, okay, which is quite big. So it means it becomes the line that cuts the curve at larger values of x looks something like this. Comes like this, nearly goes towards a vertical line, okay? But it never becomes vertical. Only the limit is x tends to infinity, right? So the main point here was we were not interested in the function value at 3. We were interested in the derivative. We were interested in derivative, and in particular in the value x equal to 3. That's why we said 2 times 3. 2 times 3 is equal to 6. Okay, so that was the question there. Right? Is that okay?
I got.
Great. Thanks for the choice. Great. So coming back to my question, guys, were there anyone that struggled with understanding the second example? Any person? Struggled with the second example again? The one that related to f of x equal to 2x, 2 times x to a half. Is there any person that struggled with that particular case? Any person? Because there is just a combination of the binomial theorem. And sorry guys, just give me, okay, student Arira, you with me now?
Yes, could you please just quickly go through that example?
Is it okay? Is there any particular step in the example that's problematic? Is it the whole example?
Just to kick it off, just to get an idea.
Okay. Okay. So basically, you invoke the binomial theorem there. So let me just share the. Can you guys see the line board there? You can see the board with the lines there. See that? Can you guys see the board, the writing board? Okay, great. Thanks. Okay, guys.
Yes, sir.
So great. So let me just open another page here, and then look at that. Okay. So it's example 2. Example 2. So fortunately, you guys have your formula sheets in the exam, so you can just refer to the binomial theorem. So there, the question was, for example 2, on page 30, they say, so f of x is given as 2 times x to a half. So it's 2 times the square root of x. Okay, and they want f prime of x from first principles, right? From first principles. So they're very specific about it. Normally, with the rules that you will learn, maybe when we meet again, we'll just soon, you'll just see that that answer is equal to x. That's all, okay? But we'll show how we get it. That's just using the rules of, so you'll see, well, it's a half times 2 times, so you will see it's 1 over 2 times the square root of x, something like that, okay? Or 1 over the square root of x. Let me see, it's a half to the minus that. So it's 1 over the square root of x, I think, yeah. That's what you'll see. So let's see if we can get that answer. But with the rules, it's much quicker, okay? Right, so let's just write down the definition of a derivative again. So from first principles is the limit as h tends to 0, f of x plus h minus f of x over h, right? So the main problem is this part here. You've got f of x, so it's the f of x plus h part. F of x plus h is equal to, so in the place of x at here, you put x plus h, 2 times x plus h. So this part here, you will recognize it as a plus b to the n, where n is a fraction now. You can assume a to be x and b to be h, okay? That's fine. And then, like we discussed the binomial theorem, then you proceed in a similar fashion, okay? Okay. So let's just use that theorem. Let's just write down what the theorem says again. Remember, you will recall that x, a plus b, let me just use a plus b because you're familiar with that, okay? Recall that a plus b to the n is equal to a to the n plus na, then it's n minus 1 b over 1 factorial. Then it's n times n minus 1 a to the n minus 2b squared over 2 factorial. And because it's a fraction in the exponent, we have to add an infinite number of terms, okay? Just look at your formula sheet there, guys. So it's a to the n plus n a to the n minus 1b plus n times n minus 1 over 2 factorial a to the n minus 1 b squared plus. It goes on, okay? So I can't write out all those terms. There are an infinite number of terms, okay? Let me just write this nicely. So if you agree that that's the formula, so it's n minus 1 here. Let's write this nicely, n minus 1. If you agree, you're happy with that formula, and this is 1 factorial, which is just 1. I don't need to write it like that, okay? Of course, after this part here with the 3 dots, I could have maybe just written an additional term there, and then say plus, okay? So I could have just written n times n minus 1 times n minus 2 over 3 factorial a to the n minus 3b cubed, and then say plus dot. Countably, infinitely many number of terms, because the exponent is a fraction, okay? And that's basically that part. But now instead of a plus b, I've got x plus h. I've got x plus h. And that is to the exponent a half, this part here. That is the problem. Leave that 2 aside. That 2 is a constant, it stays a constant. So x plus h to a half can be written as, so this is my f of x plus h. It's 2 times that. The 2 will keep outside, okay? Keep that 2 outside, it doesn't interfere. Now a is equal to x and b is equal to h. And n is equal to a half. You just substitute that and you're fine. So remember, a was equal to x, it's x to a half. Right? A is equal to x, b is equal to h, n is equal to a half. So that's all you have to do. Plus n is a half, a is x, and then x must be on top. It's not in the denominator, it's on top. And this is n, it's a half minus 1 times b, which is h. And it's all over 1 factorial, which is just 1. Plus, right? Now it's n, which is a half, times a half, minus 1, which is minus a half, over 2 factorial, which is 2. And this is x to the half minus 2, which is minus 1.5. A half minus 2 is minus 1.5, which is minus 3 over 2. And then b, which is h squared, plus. Now I come to this part here. And I hope you guys can see the pattern emerging. So it's a half times minus a half. It's n minus 1, it's a half minus a half. And here it's a half minus 2, which is minus 1.5, which is minus 3 over 2. Okay, this here is also minus 3 over 2, guys. Okay. And this is over 3 factorial, which is 6. And this is a, and this is a half minus 3. Half minus 3, which is minus 2.5. B cubed. So then a is equal to x, sorry guys. A is equal to x, right? A is equal to x, I'm writing down a. So half minus 3 is minus 2.5, which is minus 5 over 2. Minus 5 over 2. Right? And here we've got b cubed, which is h cubed, plus, right? All must be multiplied by the 2 outside. And there's your f of x plus h, okay? Written in that form. So now, you just have to now add things, subtract fractions, add fractions, and then you're fine. So we're still busy with f of x plus h, that's the main part. It's x to a half. I'm rewriting everything again nicely. Plus a half. And then there's x, half minus 1 is minus a half. H plus. Now, I credit you guys with sufficient common sense to be able to do this part here. So this is the part, a half minus a half, which is minus a quarter if I multiply that, okay? So it's minus a quarter. Let me just check where that comes. It's minus a quarter. I'm multiplying a half by minus a half, right? Over 2, which is minus 1 over 8. And this is x to the minus 3 over 2, this part here, h squared. Okay, this part here, guys, is minus 1 over 8. Okay, right. Plus, now I'm here. So it's a half times minus half times minus 3 over 2. Okay, so that gives me plus 3 over 8. But the 8 must be multiplied by the 6 in the denominator. Okay, so it's 3 over 8 times 6, which is 48. Right? And then it's x to the minus 5 over 2. And then there's h cubed plus. And those 3 dots signifies that it goes, the sum goes, it's an infinite number of terms that you're summing over, okay? Right. And this 3 over 48 is 1 over 16, by the way, okay? And remember this here, this bit here, it's minus 1 over 8, this bit here that I circled. And then you're set to go, okay? Right. So let's look at the study guide, what it says now from this point onwards. So we got the main culprit, f of x plus h. We have f of x. That's not a problem. And then we just invoke the first principles definition of a derivative of a function. That's all. So this was the problematic part, which we've just written down now. And then the rest is subtraction and division by h and letting h tend to 0, okay? Take out a common factor. So at this stage, Adir, because you posed the question, and I trust that I've covered your concerns in the interim, can we share the learning guide now, right? And let's see, because basically that's the gist of it, okay? So here's the learning guide. These are all the multiplications. So this was the part. Remember, we had 2 times that. I kept that 2. There's where we are. You see that the factor x plus h to half may be expanded by using the binomial theorem. They are all their multiplications. Can you see that? So you multiply the 2 outside by each of those terms inside there. Of course, there are infinitely many terms, but of course we wrote down 3 because there's a pattern emerging. Okay, right. I wrote down, I think, what was it? Let me just see, guys. I think I wrote down 4 terms. Okay, I wrote down 4 terms. That's fine. I wrote down more terms than what they wanted. I think it's 1, 2, 3, 4. Yeah, they just wrote down 3 was sufficient. Okay, so you didn't really need to write this down. It's a bit redundant because you'll see a pattern emerging. Okay, but I just wanted to give you the gist of the argument. Okay, right. So let me just share that learning guide with you. Okay.
Yes, I was just confused on how many terms to go on.
No, it's fine. Look, I went up to 3, but after I went up to 4 terms, sorry, they went up to 3, as you can see there, and all of those terms are there as per the binomial theorem. The point is, it was sufficient information for you to see a pattern emerging. You will see the higher order terms in h. You'll have h cubed, h to the 4, h to the 100, h to 1,000, h to 1,000,000. Okay, whatever, billion, and that exponent will tend to infinity, but it doesn't matter. Okay, this 2x to a half is no h. That first term has no h attached to it. All the other terms has h attached to it. Okay, has some power. Can you see there? Okay, and then look there. This last term here is the minus f of x part, and then you can see that those cancel, and they are left with only the terms that have the h involved as a step here. So after subtracting, and I'm talking about this here, guys, let me show you. I'm talking about this part here. They're subtracting this 2 times x to a half, and then they're subtracting f of x from there. And then that cancels to 0, okay? And they're only left with the terms that involve powers of h, as you can see there now, okay? Right. All the terms containing an h become 0. Can you see that? There's an h in the denominator. It cancels this h that they took out as a common factor. It cancels that one. They took out h as a common factor because all those countably infinitely many terms have an h factor attached to it. However, in the limit as h tends to 0, all of those terms that have an h multiplied by it will get to 0. And you'll only remain with 1 over the square root of x, which is what I predicted, okay? Remember, x to the minus half is 1 over the square root of x, right? So that was basically it. So as h tends to 0, all these terms that involve an h, doesn't matter, they go on and on. They will cancel and become 0. And so that you'll only be left with x to the minus half. That's basically the gist of that argument. Does that cover your question, Adir?
Yes, very
Okay.
well, sir.
It doesn't matter. I could have stopped after the 3rd term. I just went on, okay, to the 4th term, which was really unnecessary, okay? Because you should see a pattern emerging whereby higher and higher powers of h come, but it has no bearing ultimately because it will tend to 0. You'll take out a common factor h, and there'll only remain an x to a half there, right? And then that's the part that you're interested in. What is that part? There'll remain x to the minus half. That's the part that will remain, okay? Because that other 2x to a half cancelled, okay? Cancelled. So you only remain with x to the minus half. So yeah, so 3 terms were more than sufficient for you to see what's happening. Okay? Right. Great. Okay, guys, any other questions for clarification? Any other questions? Okay, great. Thanks, Adir. Right. So, guys, then we can look at an activity. If you can understand that problem, thanks to the Navutala. If you can understand that problem, then the other problems are really relatively simple. Okay. Right. I want us to look at the problem. Let's look at activity 1 there. And yeah, let's look at activity 1. And let's look at maybe say 2-3 problems from it. Okay. So let me just write down that activity. Let me just share the line board with you guys. Share the line board with you. So from the learning guide, let me just add this. This page, right? So from activity 1, you have this question. Activity 1, it's on page 31, okay? Activity 1, page 31. So there's this question, and it's something I just want to address as student Joyce wanted clarification on one particular problem. So here they ask you to determine, they ask you in the A part, they say determine the derivatives of the following from first principles. Determine the derivatives. So dy dx, okay, or f prime of x from first principles. Meaning the definition, if limit is h tends to 0 of f of x plus h minus f of x from first principles, okay? Right. So for the A part, y equal to 3x squared, right? At x equal to minus 2. And then for the B, the B part, it's relatively easy. Let's leave that one. The C part appears challenging, but it's not. The limit of the sum is the sum of the limits. So, but anyway, it's fine. We can use it. So f of x is equal to x minus 1 over x. Okay. And then the D part. And the D part is the same as the example that we just did now. However, here we'll have a finite number of terms, y equal to x to the h. Okay. Right. The hint says use the binomial theorem. Of course, here you'll have a finite number of terms. Use the binomial theorem, right? That's the main thing there, okay? Right. So let's look at the A part quickly. So solution. Let's look at the A part. Look at the A part. So for the A part, so let's get dy dx now, right? So y equal to f of x equal to 3x squared. So f of x plus h, because we need that. We need that in the definition, guys. Remember the definition? Here's the definition. Let me circle it in red for you. So I'm going to use this again. Okay, f of x plus h, we need this one. That first term in the denominator, in the numerator, that's the one we need, okay? So we're going to get that f of x plus h. So in the place of x, we put x plus h. Right. Okay, and now here we can just multiply this out. 3x squared plus 6xh plus 3h squared. Okay, so now dy dx or f prime of x is equal to the limit as h tends to 0 of f of x plus h plus 3h squared minus f of x. What is f of x? 3x squared. And we have to divide all of those terms, those 4 terms, we have to divide it by h. This is in the limit as h tends to 0, remember? So now there's a cancellation occurring with the first and the last the last terms. And then my common factor here is h in the numerator. The limit is h tends to 0, so we take out the h, we put 6x plus 3h, right? It's my common factor there, 6x, so h is my common factor. And then I cancels with the h in the denominator. So in the limit as h tends to 0, this is equal to 6x, because 3 times 0 is 0, 3 times h is 0, so h tends to 0, but 6x is expected. So they wanted that derivative at x equal to minus 2. So at x equal to, is it minus 2, is it? At x equal to minus 2, dy dx is equal to 6 multiplied by minus 2, which is minus 12. Okay? It's minus 12. And it makes sense also if you look at the curve. So that's a negative gradient of the tangent line. If you were to draw the graph of 3x squared, your graph will look something like this. Of course, it's not required. I just want you to have some visual perspective of this, some geometric feel of the problem. So 3x squared is a very relatively steeper than 3x, so steeper than x squared. So it will go something like this. There's the graph of 3x squared, say, y equal to f of x equal to 3x squared, say. So we found its slope. We found its slope at x equal to minus 2, which lies about here. And that slope, the tangent line behaves like this at that point. And it has a relatively steep negative gradient of minus 12, okay? So at x equal to minus 2, that's the situation there with the function y equal to f of x equal to 3x squared, okay? Right, so that's what basically happening there. Right. Any questions there, guys?
Dr. Sears.
Okay, okay.
I'm just wondering, I know if you use like the method that you described before, you multiply the coefficient with the
binomial
no the formula, the quick way, where you would multiply the coefficient by the exponent, you'd get that 6x. But now I'm just wondering, as the way that you're solving it now, you have 6x plus 3h squared.
6xh, yeah. 6xh, yeah.
Yeah, 6h. Yes. So if you were to factor out 3h as a common factor, you wouldn't reach the same answer.
No, it would be. You see, you just wait. Make sure you write down all the terms in the numerator, and then you see, wow, but I'm subtracting out this, so that's f of x plus h minus f of x. There's my f of x. I'm subtracting the f of x as per the definition here. Remember, there's a subtraction occurring in the numerator of f of x. So I multiply out whatever f of x plus h gives. I multiply that out. Then I subtract f of x, and then I resort to factorization only after that. Okay, to multiplication. Sorry, to multiplication, and then I say okay. And then I said okay, there's a common factor there, and I have a denominator h. So let me do the cancellation. Okay. And then I let h tend to 0. So 3h goes to 0 because h goes to 0. So 3 times 0 is 0. And I only remain with 6x. Okay. Right. And what that gives you, that dy dx equal to 6x, gives you the general equation for the slope of a tangent line to the curve y equal to 3x squared. Or it gives you the general equation for the derivative of the curve 3x squared at any point x. So for example, you can ask me, what is the derivative of that curve at x equal to 1 billion? You just say 6 times 1 billion. Because remember, the domain of this function is such that it covers all the real numbers, okay? So you can see that as x tends to infinity, the gradient becomes bigger and bigger. As x tends to infinity, that curve goes up. Okay, so the gradient, that line becomes steeper and steeper. It tends to a vertical line. It tends to infinity. On the other hand, as x tends to negative infinity, it goes to negative infinity this way, you will see that curve shifts up that way. It shifts up. So that far away from zero, the slope of a tangent line will almost be like vertical. Be almost vertical. It also tends to minus infinity, that slope. Okay, right. So I just wanted you to have some geometric feel for that. That's why I drew that stuff in there. Okay, so that you can see it makes sense visually. Okay, right. Okay, thanks for that question. Any other compelling questions, guys? I want us to look at problem number C. Are you guys okay with that? Problem number C. Okay. Let me. So we're still sharing that line board. So problem C asks for. Problem C asks for this one here. Right? Determine the derivative from first principles. And remember the first principles. I write down the definition again. So for C, let me just open this. So the C part. Right. So we have, remember, I'm just writing down the definition. First derivative of f at x is equal to the limit as h tends to 0, f of x plus h minus f of x over h. Okay? Over h. Right. And then our particular function is the curve f of x minus 1 over x. Right? Right. So we are compelled to give this one. So we want the derivative of this function. So we need f of x plus h. We have f of x already. Here's it. We need f of x plus h. So f of x plus h. So in the place of x, I put x plus h. Right? That's what we do there. So we can look at it like that. Right. So there's a number of approaches we can look at here. We can maybe take, we can perhaps take the numerator here, the LCD, the least common denominator of the two, which is x plus h, right? Because we have a fraction here, and then x plus h times x plus h is x plus h squared minus 1. Okay, hope we can be able to deal with that one. Shouldn't be a problem, but our final answer should be 1 plus 1 over x squared. That's our final answer that we're expecting if you use the laws of differentiation. Okay, that's our final answer that we should get as far as I can see. Yes, yeah, it should be our final answer. Okay, so there is f of x plus h. So in the place of x, I put x plus h. Now I get the LCD, which is x plus h. 1 goes in x plus h times x plus h. It's x plus h squared. And x plus h goes in there once, and it gives me that. Okay, so there's f of x plus h. We've got f of x. Right? We've got f of x. Thus, now I apply the definition. Right? And now I'm going to substitute. I'm going to substitute directly, okay? So f prime of x is equal to, now there's my f of x plus h. The limit is h tends to 0 of f of x plus h, which is x plus h squared minus 1 over x plus h minus f of x, which is x minus 1 over x. And all of this must be divided by h. Here in the definition, in the denominator, there's my h. Okay, so all of that must be divided by h. Right? So let us deal with what's happening here. Let us deal with what's happening here and see what we can come up with. Okay, so limit h tends to 0. So let us see very quickly. So I can get my LCD here again. Let me try and fix up this mess here, and then let's see what we can do there. Okay, right. So So what I can do here is say x plus h all squared. I'm trying to avoid the binomial theorem here, guys, okay? So just bear with me. I hope I don't need to apply it. And then minus x minus plus 1 over x. I'm multiplying that out, and it's all divided by h, okay? All divided by h. Right, let me just see if they have used the binomial, because if I don't use it, I may end up in trouble also. I think it was problem C, and I'll tell you why. Yeah, they didn't use it there. They didn't use it, okay? So that's okay. So f of x plus h minus f of x. So what they do is, guys, they don't actually, they keep it like this. They don't actually make it to be one term, as I can see here. They don't do this, what I did here. They keep f of x plus h like that, as x plus h minus 1 over x plus h. And then they just subtract from there x minus 1 over x. That's all they do, okay? And then at the end, they put things together. Then they get the LCD, okay? So they don't resort to this. They actually keep this. So I just went a step further, which is not really necessary because it can be a bit of a roundabout way, okay? So they keep the f of x plus h like that. They stop there, they didn't go further. Unlike me, they stop there. And then they subtract the f of x from there, okay? So I'm going to try and do what they did there. Sorry for that, guys. So instead of that, because they can see there's going to be a big problem, but we still have to do fractions. So let's write down f of x plus h. Here's my f of x subtracted, okay? So let's write down x plus h minus 1 over x plus h. Then we can get rid of other terms maybe quicker, okay? Right. So let me just get rid of this mess here. So they didn't do that, they didn't get the LCD there for the f of x plus h. So they just stopped right here where I started. Okay, they just stopped here. So I'm writing that part down. Right, so let's see. Now, let's sort out the numerator quickly. Let's sort out the numerator quickly. So it's x plus h minus 1 over x plus h minus x plus 1 over x. And that's all divided by h. And then there's a subtraction happening there, okay? Great. So now there are less terms to work with in the numerator. And now I suspect they get the LCD now only, and then they combine those terms. And the LCD there is x times x plus h, okay? I'll show you now. Look at the numerator, guys. Let me write down the numerator. H. Let's just see what remains there over 1 over x plus h plus 1 over x. And now they get the LCD of these ones here, of the last two terms. They get the LCD of that there, okay? Right. And then they also use that h, that's fine. They also use that. So the LCD there is x times x plus h. Yeah. Let me just show it in red. This part here and this part here. Of course, this is h over 1 there, so that's okay. Right? Don't worry about the h in the denominator now, okay? So let's see quickly. So it's the limit as h tends to 0. Let's get our LCD for the numerator, okay? It's x plus h times x in the numerator now, okay? Leave that h in the denominator. Leave this h there. Let me just write it nicely here, guys. Leave that h in the denominator. Don't touch it. It's fine. We're now in the numerator. So h goes in there once. So 1 goes in there, x plus h times x. So we multiply that by h. So we've got h, x plus h times x minus x plus x plus h. That's in the numerator, okay? Just writing this nice, okay? So let me just remind you guys, this h, here's it. I'm checking the LCD of x plus h and x. The first h has a 1 in the denominator. My LCD for the numerator is x times x plus h. Now I'm dividing 1 into there, right? and I multiply that by h. So now I multiplied h by x and x plus h. Now x plus h goes into x plus h once, so, and there's an x there, so it's minus that x. And x goes in x times x plus h times, right? You guys must just double check the calculation there. So h goes in there, 1 goes in there, x times x plus h times, right? And then we multiply that by h, and then x plus h goes in there x times, and then we multiply x by minus 1, so it's minus x, and x goes in there. And look at that cancellation happening again, guys. There's another cancellation. Leave that h in the denominator for now. It doesn't interfere with us, okay? So, and now, at this stage, we should be looking for common factors occurring, okay? And let's just see what they do. Of course, this denominator here will go down and be multiplied by that h. If I say to you guys 3 over 2 divided by 2, you will tell me it's 3 over 2 times 2, which is 3 over 4. So, so that's what will happen. So we will shift this x times x plus h to be multiplied by h in the denominator, okay? Right. Let's just open another page there. So, so now I'm doing that multiplication. So currently, so they leave it till the end, guys, okay? They leave it till the end. They first work with it. I'm working with both of them simultaneously. So let me see what they wrote. So currently we are here currently, the limit. So they did it separately. I'm doing it together. So I got x squared h, and I'm multiplying out. I'm multiplying out now, guys, x squared h plus xh squared. There was already a cancellation there with the x's plus h. So I'm multiplying the bracket here on top out, guys, okay? Hx squared, h squared x, right? The x is cancelled. I'm left with positive h, right? And then what I'm going to do to avoid confusion, write x times x plus h, and just this h here, I'll write it here, 1 over h. It's the same thing. Okay, it's exactly the same thing, right? Okay, great. So let's just see what they have here. So you guys will see there's a common factor appearing. There's a common factor appearing there. Okay. So we can take out h there in the numerator. Yeah. Common factor h, and then you'll see it will cancel with this h here. So we don't let h tend to 0 yet. Let's just take out the h. X squared plus xh plus 1 over x times x plus h. And there's my other h that was in the initial denominator, okay? Now there's that cancellation happening. Now let h tend to 0. Let h tend to 0. This becomes 0. This becomes 0. So we've got x squared plus 1 over x squared. Right? Remember, h tends to 0 now, so this becomes 0. X times h becomes 0. I'm left with x squared plus 1 in the numerator. And then I'm left with x times x, which is x squared. And when you divide x squared into both, you get 1 over 1, which I said to you initially is the answer that we expect. 1 plus 1 over x squared, which is what I wrote down on the side here. Right? But there I just use the rules of differentiation. Okay. But of course, you don't know that yet unless you've prepared ahead, which is good. But from first principles, what you have here, you have the derivative of y with respect to x. Okay. That's what you have. Okay, guys. Any questions there? Any compelling questions that you have? So that was a very nice example. They did them separately. They did f of x plus h. And then later they introduced minus f of x. And then afterwards they divided by h or multiply. People, if I multiply by 1 over h, I'm dividing by h, okay? If I multiply by 1 over h, if I say 2, I am multiplying by half, I'm dividing by 2, okay? So that means the same thing. So that's how they got that answer. They did it separately. Mine was a bit more compact. Maybe you prefer to do it separately, but I was just worried about time there, okay? I would like you guys to look at example activity 1B on your own. Like it's just an employment of the binomial theorem again, okay? Just the binomial theorem. You will see that f of x plus h is x plus h to the 8, okay? And then you can just compare your responses, okay? Right, so what I want to know from you guys now, because I would really like us to deal with standard forms in differentiation, I would like to know if there were any problematic problems from your assignments, maybe that I can guide you on, particularly from first principles, or any other work after this, okay? Any other work. So I just want to have some questions from you guys, because my expectation was that you guys by now would have started with integration already, okay? Which is the inverse process of differentiation. So any questions there, guys? Any questions? Okay. Okay, so I think the only outstanding problem on the definition of the derivative from first principles was that activity D, which is a nice one, invoking the binomial theorem there, okay? So I think that was sufficient. If you can understand how to use the binomial theorem in the first principles definition of a derivative, and looking at that example that we did, I think example 2, that Adir asked me about, student Adir asked me, then you're fine if you understand those ones. Those are usually the hectic ones, okay? Right. So I want to share the following with you quickly. And I was really hoping you guys would work ahead, and then, because remember we started only in April with this work, so I was hoping to answer some questions in later sections also. Right. So we came up to we did this one here, the initial example 2, and then we just finished some problems from activity 2. We completed A and C, and I would like you to guys look at D, and I was hoping you would have looked at D already. And then this is the part that's basically it uses the first principles definition to prove certain things now, rules of differentiation, okay? But in your formula sheets, you'll have these standard forms. And this is the statement in the first paragraph. They say the process of finding the derivative is called differentiation, and deriving it via the limit is called differentiation from first principles. The definition that I wrote down, the limit of f of x plus h minus fx over h as h tends to 0. It is quite an involved process, and to avoid having to evaluate limits every time we differentiate, we used established derivatives called standard forms, which comes from first principles, okay? Right, so they say you must memorize this list. And in the forms in which the derivatives are given, it is essential that the angles be measured in radians. So it's not in degrees, okay? Right. The standard derivatives summarized below may be proved theoretically using the first principles and are true for all real values of x. Notice that the list includes derivatives of the trigonometric functions also. So there we've got, and we can prove these, all of these things can be proven using the first principles definition. So if y is a constant, the derivative of y with respect to x is 0. Let me show that case for you just by visualization, okay? Just by visualization. We can prove all these things using the binomial theorem and the first in conjunction with the first principles definition. So here, suppose y is a constant, then the derivative of y with respect to x is 0. Okay, what does that mean? So to reiterate, guys, so these are the standard derivatives, the standard functions. So if y is a constant, the first derivative of y with respect to x is 0, which means there's no change in y. Okay, there's no change in y with respect to x. So for example, let's construct a constant function. Let me share the line board with you guys, okay? Share the line board with you guys. Let's see quickly. So there, y is a constant function. So for the first case, so this is our standard form. Standard forms, okay? Right. So suppose y is a constant function. So y is equal to k, a constant, any constant. Okay, so f of x equal to y is equal to constant. They say that f prime of x or dy dx is equal to 0. So let's draw any constant function in the Cartesian plane. Let's see. Let's draw any constant function in the Cartesian plane, okay? Any one that you can think of. We will be consistent and call it, we can be y equal to 4, y equal to 4,000, y equal to minus 4 million. Doesn't matter, okay? So there's the Cartesian plane with the y, the vertical y-axis and the horizontal x-axis. And let's suppose we draw some line y equal to k. Right? Maybe just to show the fact that it doesn't change, let me draw this. So it's parallel to the x-axis, this line y equal to k. Right? It's parallel to the x-axis. And suppose this is y equal to k. This is the line y equal to k. There's the k value. This is the line y equal to f of x equal to k. And you guys can see that no change occurs. Y stays at y equal to k. No matter how x changes to the left or to the right, y stays at k. Therefore, we say the first derivative of y with respect to x is 0. There's no change occurring. There's no change in x. The change in y, so what happens here is the change in y is 0. X can change no matter how x changes, the change in y is 0. There's no change in y, it's constant throughout, from minus infinity to positive infinity. For x lying between minus and positive infinity, y stays at k, doesn't matter. So that derivative, that gradient of that line is 0, which means the first derivative is 0, okay? And that's how they got to this result in the guide, okay? Of course, you can prove it using first principles, but I just wanted you guys to see it visually for a constant function. And this is the result in the second column there, okay? I trust that you guys can see the standard forms. And look at number 2 there. The derivative of x with respect to x is 1. And the derivative of x to the n is nx to the n minus 1. You can prove all these things using first principles. And then the derivative of ax to the n is anx to the n minus 1, okay? Right. And then there's the exponential function also. I'm not sure if you guys have encountered that one yet. The derivative of e to the x is e to the x. The only function that has that property. And there are a number of functions, y equal to log x base a. And you can prove some of these things that are relatively easy. They are the trigonometric functions. The derivative of sine k is a constant, kx is k cos kx. And the derivative of cos is minus k sine kx. And the derivative of tan is k sec squared kx. And cot is minus k cosec squared kx. And the same for sec, it's sec tan. And that k multiplied in the front. For cosec is minus cosec cot. And then there's the k in front, okay? So those are the ones that we will look at. So what you will do is in your tables, you will refer to those standard forms in your formulas that you have there, but they say that you must memorize this list, okay? You must memorize it. It saves you time, okay? Saves you time. So that's very important to note. So I expect you guys to memorize this list. If y is equal to a to the x, the derivative is a to the x ln a for the logarithmic function, okay? Right. Of course, like I said, you can prove these things using first principles and other methods also, okay? Right. So the first one they give you, let's see quickly. Let's do example 1, okay? So example 1 is on page, let's see the guys. Example 1 is on page 36. Page 36. You can see that y is a constant. The derivative of a constant is 0, as we expected. I just drew the graph for you of y equal to k, and we saw that gradient was 0. The slope of that line, 0. And here, for the b part, so you have kx. So there we use what we call the power rule, okay, for that one. So let's maybe do a few examples, and then I refer you to you should have your formula sheets in front of you, but of course it's better that you must memorize it actually, okay? So you can look at examples. I want us to look at some activities now, okay? I want us to look at some activities, activity 1 in particular, okay? So let's see that quickly. Then I will refer you to the standard form. So let me keep the standard form there. The standard forms, there they are. I'll keep that on the screen. And then let's look at some examples. Let me share the line board with you, and we'll look at activity 1. Activity 1. Activity 1. Where's the line board now? Oh, great. Let's see, okay. We still have about 15 minutes, so let's just see if I can open another page here. Right, so I want you guys to memorize those things, and then work will get done much faster if that can be done. So for activity 1, so for activity 1, they have the following. They say determine dy dx of the following. Okay, so this is on page 37, guys. There are a number of problems here up from A up to P. I'm just paraphrasing. Determine dy dx, okay, for the following. Right, so the A part, they say x to the 5. The B part, sine square root 3x. C, let's do a number of them. C, it's cot 2x. D is equal to the cube root of x. And E is equal to log of x base 10. F is equal to ln of 3x, the natural log of 3x, so this is base E, and G is e to the minus 5x. The H is 5x to the 6, so y is that, so you put y equal to that, and then I is equal to 10 3x, so there's my k is 3 is a constant, and J is 10 to the x, and K is cosec x, and L is equal to log of x base 3. Right. And then M is equal to x to the 3 over 4, while N is equal to 6x to the 10, while O is equal to x to the 4 over 4. P is equal to sec of x over 2, secant of x over 2, okay, sec. Right, okay guys, so this is what we'll do, okay? So we will look at these problems, look at all these problems, and every time I will then, so this is y. So call all these functions y, so we get dy dx. So let y be that. So they're all called y. So then we can get the y dx or f prime of x. So you can call them f of x. It doesn't matter. Okay. Y equal to y equal to y equal to y equal to and y equal to, yeah, let me just erase this part. So then we can get the y dx straight away. And then this is p, ne? P. Right. Okay, guys, so I can, let me try and give you this answer, okay? Thus, so I'm just going to do the solutions next to it. This is like your n is equal to 5, okay? So for this case here, n is equal to 5. So if you look at the derivative of x to the n, say y is equal to kx to the n. They say it's equal to nk or kn x to the n minus 1, right? And if you look at your formula sheet, let me just share the formula sheet. I'll show you which one I'm going to use. Let me just share your formula sheet. Of course, you guys must memorize this. The one I'm referring to is this one here, k is equal to 1. Look at number 3 there, guys. Look at number 3. I said kx to the n, but k is 1, so it's okay, right? So it's n times x to the n minus 1, where n is a constant. Oh, here's number 4. Number 4 is more applicable. I use k instead of a. Look at number 4. So we add x to the 5. So for x to the 5, n is 5 and a is 1. Okay, so there's number 4. So we apply rule number standard form number 4 for that one. So let me share the line board with you guys again. Let me see, there's the journal. So there's it. So I'm doing this one now. A is 1 and n is 5. So it's 5x to the 5 minus 1. It's 5x to the 4. Right, there's that one. For this one, well, the derivative of sine is cosine, okay? But now it says the following. It says that if y is equal to sine kx, then dy dx is equal to k cos kx. Let me share the formula sheet with you guys again. There's sine. There's sine. There's sine. So it's sine kx. There k is square root of 3. Look at number 10 there, guys. Look at number 10. So it's the sine. We need to differentiate the sine of square root of 3x. K is equal to square root of 3. Okay, k is the square root of 3 for our problem. So look at number 10. Let me share the line board again. Share the line board with you. Right. There's it. So sine y dx is equal to square root of 3k cos kx. Right? Square root of 3 times the cosine of square root of 3x. Okay? Right. And then for cot, okay, for cot kx, so if y is equal to cot kx, then dy dx is equal to k minus cos x squared kx. Let's see that one in the formula sheet. Let's share that with you guys. And the expectation, like I said, guys, is that by now you should have it in your heads, those things, okay? There's the formula sheet. There's Scott. Look at number 13 there, guys. Minus k cosec squared kx. Okay. Minus k cosec squared. Right. So we had got 2x. Okay. So 2 is equal to k. So it's minus 2 cosec squared 2x. So for our k is a constant, number 13. Okay. And to us, it was 2. So this is it. But we had, for our number was number C, I think. C, okay? Right, there's it. So look at number C there, guys. dy dx is equal to 2 minus cosec squared minus cosec squared 2x minus cosec squared 2x. There's it. Okay. And then for this one, you can first write it maybe in third form, right? Write it in exponential form, in power form. So x to the 1 over 3 plus here, and you guys must have that formula sheet ready. Y dx is 1 over 3 x 1 over 3 minus 1, which is 1 over 3. You can refer to your formula sheet again, guys. So it's x minus 2 over 3, okay? You can leave it like that, or you can write it in third form. It's up to you. It's entirely up to you. It doesn't matter, okay? Right. You can say 1 over 3, and then you can write it like this. Let me just write it nicely, you guys. Nice. 1 over 3 multiplied by, and then you can just say it's the cube root of x squared. Cube root of x squared. Okay, you can also write it like that, or you can just leave it like this. Okay, and this one comes from here. Let me just share that standard form with you. Let me just try and find that standard form, guys. So just see that standard form. X to the n. So it was, I think it was in our case, it was x to a third, yeah, x to a third, okay? So x to a third is a third, x to a third minus 1, okay? Yeah, so that was fine. So I just used that third one, okay? I don't think there's another one, but that one incorporates what I've explained to you just now, okay? What page is that? Page number 37. Page 37. So that's how you guys should know these things. And it's faster rather than going back and forth to the formula sheet, okay? So the one that I just got now, the cube root of x, the derivative of that, I wrote this in it. Look at number 3 there. I wrote it in exponential form, x to a third. So it's a third x to the n minus, so the third is n, a third minus 1. And then if I look back at what I got in Zano, I wrote down for the Zano, this is what we got. Okay, there's it. Of course, you can leave it with a negative exponent, or you can write it as a positive exponent like this, in third form. Okay. Oh, sorry guys, I needed to write this as 3, not 1 over 3. So write this as the cube root. Right, this is the cube root. Yeah. So a third times 1 over the cube root of x squared. That's the proper way of writing that. Okay. Right. And then for this one, so for this one, there are a number of ways to do this without using the formula sheet. But if you stuck to their formula sheet, they write the following result down. Just write down what they write. So this is the form, and we will stop at this one, and you guys can look at the others. So this looks as follows. Look at in your formula sheets, maybe on page 35, you can look at number 9 there. There they give you log x base a. So they want the derivative of that. They say it's 1 over x natural log of a, okay? And for us, a is equal to 10, and there's my x. So it's 1 over x ln 10. So there's it. There's the derivative 1 over x natural log of a. So we've got x and a is 10. Okay. So our answer would be using that result. And then we've got base 10 there. They don't write that. So our answer would be 1 over x ln 10. Okay. 1 over x ln 10. Right. That's the log of x base 10. 1 over x ln 10, where a is a constant, 10 is a constant. Okay. So you guys can go through those examples and from the activity, sorry. They're relatively straightforward if you just apply your standard forms. But you guys need to memorize these things also, right? Okay, guys, any questions now? Any questions? I did it using 3. So which question was this, student Joyce? I did it using 3 and I got the same answer. I'm not sure which one you're referring to.
It was activity number 8.
Activity A.
X
Activity A. Let me just see. For number, is it activity 1? Activity 1?
Activity 1.
Number?
A.
No, but
The A.
no, then if you use 3, if you say you use 3, oh, you mean you use the form 3. Okay, yes, use the form 3. Yeah, it's fine. 5x, yeah, it's exactly that form, yeah. X to the 5 is 5x to, yeah, that's the one that we use, right? Which is the same thing that I used, right? Same thing. Okay,
Yes.
great, yeah. That one is called the power rule. It's called the power rule, okay? Right. But they all come from, well, that one can be derived using the binomial theorem also for x to the n, okay? Right, guys, any other questions then? Any other questions before we close? Any questions there, guys? Student Joyce, number 3, number 4, they're basically the same. It's just that